Welcome to Problems and Solutions. Today we will solve a problem suggested by one of our subscribers. The problem is the problem 8 of chapter 10 of Halliday and Resnick Fundamentals of Physics. I will read and then we'll solve this problem. The angular acceleration of a wheel is alpha equals 6 times t to the fourth minus 4 times t squared, with alpha, the angular acceleration in radians per second squared, and time in seconds. At time t equals 0, the wheel has an angular velocity of 2 radians per second and an angular position of 1 radian. Write expressions for A, the angular velocity, and B, the angular position as functions of time. Okay, the problem is not difficult, but it's necessary to know a little bit of calculus to solve this problem. We know that we can write, we can write that acceleration alpha equals, the definition of the acceleration is a variation of the angular velocity, in this case, with time. Therefore, we can write that a small variation of the velocity equals the acceleration times a small variation of time. And then we can integrate this expression in time. Therefore, we can write that the integral of the angular velocity equals the integral of acceleration with time. And we'll integrate from in time from 0 to a time t. And therefore, here we'll have an initial velocity and the velocity in time t. Therefore, we will have the angular velocity minus the initial angular velocity, that is 2 radians per second, equals the integral of alpha, of the angular acceleration. That is, we have here the angular acceleration 6 times t to the fourth minus 4 times t squared, integrated in time. Therefore, here we can put this 2 in the other side of the equation, and we write omega equals, here we have 6 integrating t to the fourth, it will be time to the fifth divided by 5 minus 4 t to the third divided by 3 plus 2. And here is here we can put this a little bit here. Okay, here we have the angular velocity as function of time. In the same way, we can write that the angular velocity equals a variation of the position, angular position, with time. And therefore, we can write that a small variation in the position equals the angular velocity times a small variation of time. And we will integrate this equation, and we will have the integral of the angular position equals the integral of the velocity with time, and time will vary from 0 to t, and here we have the initial position and the position in time t. Therefore, we will have theta minus theta in the position when time equals 0, there is 1. So here we have minus 1 equals Here we have the integral from 0 to t of the results of the item A. Here, A. So here we have 6 divided by 5 t to the 5th minus 4 divided by 3 t to the third plus 2, not minus, and integrate in time. Okay, so we can put this one in the other side of the equation. So here we have 6 divided by 5 t, integrating it will be 6 divided by 6 minus 4 divided by 3 times t to the 4th divided by 4 plus 2 times t plus 1, the one that was here in the other side of the equation. And here we have the position as function of time. You can simplify this before finalize the problem, because you can cancel this and cancel this. So we will have theta as a function of time will be t to the 6th divided by 5 minus t to the 4th divided by 3 plus 2 times t plus 1. Okay. And here we have item B, B, and therefore here we have the problem is solved.